one of physics' biggest puzzles, isn't it?
No, absolutely. It's a huge one.
How to finally bring together quantum mechanics. You know, the theory of the super tiny, the weird subatomic world with general relativity. Einstein's masterpiece.
His explanation for gravity, the cosmos, yeah.
And general relativity, I mean, it's incredibly accurate, right? It predicts light bending, gravitational waves, amazing stuff.
Astonishingly accurate. Its track record is phenomenal.
But it still leaves these massive questions hanging, like what is dark energy? This thing accelerating the universe's expansion.
Exactly. GR predicts expansion, but the acceleration needs something extra. Something we call dark energy, but don't really understand.
And then there's the big one, it just doesn't seem to mesh with quantum mechanics at all.
That's the fundamental roadblock. Two incredibly successful theories describing different scales, but they don't speak the same language, mathematically or conceptually.
It's like having these two amazing blueprints for reality, but they just don't fit together.
Precisely.
So our mission for this deep dive is to dig into some really intriguing, maybe even ambitious, new ideas tackling this. We've gone through the sources you sent us, pulled out the key bits.
Trying to make sense of some cutting-edge thinking.
Yeah, give you a shortcut into these pretty mind-bending concepts. We'll look at something called the river model of general relativity. Sounds intuitive.
It's a helpful analogy.
And then dive into something pretty radical. The decoherence-determined time flow theory, DDTF.
DDTF, yeah. That one's definitely proposing a big shift.
Okay, let's break it down. Where do we start? Maybe with Einstein's picture.
Absolutely. To see where we might be going, we need to understand the foundation. Einstein's general relativity, GR, published back in 1915.
A long time ago, but still our best description of gravity on the large scale.
Right. And its core idea completely changed everything. Space-time.
Not space and time, but space-time. One thing.
Exactly. Fused together. A four-dimensional dynamic unity. 3 space dimensions, 1 time dimension, all interwoven. And it's not static.
It's not just the stage, it's part of the play.
That's a great way to put it. It's an active participant. Flexible. Bendy, even.
So gravity isn't a force pulling things, like Newton thought.
Not in GR, no. Gravity is the curvature, the distortion of this space-time fabric. Mass and energy cause the distortion.
Ah, the classic bowling ball on a rubber sheet analogy.
That's the one. The bowling ball makes a dip, and a marble rolling nearby follows the curve of the sheet. It looks like it's attracted, but it's just following the shape of space-time.
The straightest path in curved space. Geodesics, right?
Precisely. Geodesics. That applies to planets, light, everything moving through space-time.
And GR predicted the universe is expanding.
It did, which was later confirmed. And then, the shocker discovering it's not just expanding, but accelerating.
Which leads us back to dark energy, that mysterious push.
Right, something GR doesn't inherently explain.
So the advantages are clear, incredible accuracy, verified predictions like light bending, Mercury's orbit, gravitational waves. It works.
It works remarkably well. Unparalleled success in its domain.
But the limitations are also glaring. Doesn't unify with quantum mechanics.
The biggest one, arguably.
Doesn't explain dark energy or dark matter, which is what, 95% of the universe?
Roughly, yeah. The stuff we can explain with GR and the standard model is only a tiny fraction.
And GR treats space-time as fundamental. Like it's just there, not something that comes from somewhere deeper.
Exactly. It describes space-time's behavior, but not its origin. These limitations are what really drive the search for new physics.
Okay, so GR is this amazing, powerful framework, but it's got these gaping holes. And visualizing curved space-time is, frankly, still hard.
It's very abstract, absolutely.
How do we make that feel a bit more, I don't know, tangible, especially if we want to go beyond GR?
Well, that brings us neatly to the river model of general relativity. It's not a fundamental theory itself, more a mental picture.
An analogy.
Exactly, a really helpful one for intuition. Imagine space-time literally as a flowing river.
Okay, I can picture that.
Now, things with mass and energy stars, black holes, they aren't just floating in the river. They actually create currents, or maybe whirlpools, within the river's flow.
So they affect the flow itself.
Right. And other objects, like planets or even light beams, they get carried along by these currents. That's what we perceive as gravity.
So instead of being pulled by the star, the planet is just going with the flow of space-time around the star.
Precisely. It demystifies the action at a distance idea. Think of a black hole. The river flows so fast towards it that beyond a certain point, the current is faster than anything can swim against it. Escape is impossible.
that does make it easier to visualize. It emphasizes that space-time is dynamic, moving, not static.
That's its main strength. Intuitive visualization, emphasis on dynamism. It can simplify thinking about certain things.
But it's just an analogy, you said. What are its limits?
Well, it doesn't explain why the river flows or why mass creates currents. It's descriptive, not explanatory at a fundamental level. It's a visualization tool, not the physics itself.
Got it. Helpful picture, but not the whole story. Okay, so here's where it gets really interesting then. If the river model helps us visualize, what about a theory that tries to explain the why? The reason the river flows, the nature of space-time itself.
And that's where the decoherence-determined time flow theory, DDTF, comes in. It's a much more radical proposal.
Radical how?
It proposes a completely different foundation, an ontological basis for space-time and gravity. It's saying they aren't fundamental at all.
Not fundamental. Wait, so space and time aren't the basic building blocks?
Not according to DDTF. It claims they are emergent phenomena. They arise from something deeper. Quantum decoherence.
Okay, hold on. Quantum decoherence. Big term. Can you break that down? What is that in simple terms? How can information build space-time?
Right, good question. It's crucial. So, quantum mechanics allows particles to be in multiple states at once, like being in two places or spinning both ways. A superposition.
The famous quantum weirdness.
Exactly. Decoherence is basically the process where that fuzzy quantum possibility interacts with its environment, gets measured in a sense, and snaps into one definite state, one reality.
Like a quantum choice being made.
Sort of. It's the transition from quantum possibility to classical actuality. Think of a spinning coin in the air, could be heads or tails until it lands. Decoherence is the landing.
Okay.
DDTF says each of these landings, these decoherence events, acts like a tiny information node, a moment where possibility becomes reality. And it's the continuous stream of these events, countless trillions of them happening constantly, that actually weaves the fabric of space-time.
Whoa. So space-time is being constantly created moment by these quantum events.
That's the core idea. Space-time is generated by decoherence.
So where does gravity fit in, if it's not curvature?
In DDTF, gravity reflects the local density of these decoherence events, these information nodes, where you have lots of mass or energy, you get more quantum activity, more decoherence events happening more frequently.
So space-time is denser?
Yeah.
Or thicker, near mass?
Exactly. A higher density of these entropic information-creating events. That higher density is what we perceive as stronger gravity.
And time. The name mentions time flow.
Yes. DDTF suggests the rate time flows depends on this decoherence density. Specifically, it's inversely proportional. Meaning where decoherence is denser near a massive object, where gravity is strong, time actually flows slower.
Ah, that sounds like gravitational time dilation, the thing Einstein predicted, where clocks tick slower in strong gravity.
Precisely. DDTF claims to offer an underlying reason for gravitational time dilation, linking it directly to the density of these fundamental quantum events.
Okay, my mind is slightly blown. Space-time and gravity emerging from quantum snaps. That's huge.
Yeah.
Does this genuinely offer a path to unifying QM and GR? Or is it just another analogy?
It absolutely aims for unification. That's one of its main claimed advantages. By making space-time and gravity consequences of a quantum process decoherent, it naturally attempts to bridge that gap. The macro world emerges from the micro.
So it provides a why, not just a what.
That's the goal. An ontological explanation, a causal mechanism for space-time and gravity rooted in quantum information. GR describes what happens beautifully. DDTF tries to explain why it happens.
What about cosmic expansion? How does that fit?
Well, if space-time is constantly being generated by decoherence, then the universe expanding makes intuitive sense, doesn't it? New space-time is always being made.
Yeah, okay.
And it goes further. It offers potential explanation for accelerated expansion for dark energy.
How? Without needing some weird extra energy field?
The idea is, as the universe expands, there's just more space for decoherence events to happen. More volume means more opportunities for these quantum possibilities to collapse into reality.
Like a feedback loop. More space, more decoherence, faster creation of space, even more space.
Exactly. An accelerating rate of space-time generation, driven by the quantum process itself, not by some mysterious energy density. That's the claim.
And cosmic voids, these huge empty patches.
DDTF argues they aren't truly empty. There's still low-level quantum field activity, still decoherence happening, just much less densely. So space-time is still being generated everywhere, continuously, driven by this entropic process of information becoming concrete.
Okay, now the sources also mention claims of heightened conceptual clarity and greater mathematical simplicity compared to GR. That feels like a bold statement.
It's bold, especially given how elegant GR's equations are often considered.
Right, how can deriving everything from quantum decoherence be simpler?
The argument, as I understand it, is that by tracing space-time and gravity back to one fundamental process, decoherence, you might avoid needing extra spatial dimensions like in string theory or complex structures like in loop quantum gravity. The complexity shifts from geometry to quantum information. Whether it's truly simpler mathematically is still very much up for debate and requires rigorous development.
And then there was that phrase, theopoetics of reality. That sounds unusual for physics.
It's extremely unusual. You don't typically see physics theories branching into philosophy or theology like that.
Is it trying to make religious claims?
I don't think so, not directly. It seems more like an acknowledgement that if the theory is right, if reality literally emerges from these information events, it raises profound philosophical questions about creation, existence, and the nature of reality itself. Questions that might resonate with theological or poetic ways of thinking about the universe's origins. It's definitely pushing boundaries.
Okay, incredibly ambitious.
Yeah.
Tackling unification, dark energy, the nature of time. But it sounds very new. What are the downsides, the hurdles?
Oh, significant hurdles. Primarily, it's novelty. It's radical, it hasn't been around long, hasn't faced intense experimental scrutiny or gained widespread acceptance. That's the biggest thing.
It needs testing, proving.
Absolutely. And it requires a huge mental shift. Thinking of space and time not as fundamental, but as emergent. That's tough, even for physicists.
We're so used to them being the bedrock.
Exactly. And then there's the challenge of making unique, testable predictions. GR is so good at explaining what we currently observe. DDTF needs to predict something specific, something different that we can actually go out and measure to distinguish itself. That's hard.
Right. So let's connect this back. How does DDTF, this emergent idea, relate to the intuition of the river model? And how does its idea of attraction differ from Einstein's curvature? You said the river model flow feels like attraction.
Good question, tying it together. DDTF isn't just trying to harmonize with GR, it's trying to explain GR from a deeper level. GR describes DDTF aims to be the why.
Okay.
But with the river model, there's a really nice synergy. Both emphasize dynamic spacetime. The river model becomes a great visual metaphor for DDTF. The flow is like the continuous generation of spacetime from decoherence.
And the currents around mass.
That's like the increased density of decoherence events that DDTF proposes. Where the river flows faster or has stronger currents, gravity, it represents that denser region of spacetime generation in DDTF. So the analogy holds up quite well as a visual aid.
So how does the river flow towards mass if it's not curvature? And are things really attracted?
Right. In DDTF, it's not geometric curvature causing the flow or attraction, it's this ontological difference, the difference in the density of space-time generation itself.
The thickness we talked about.
Exactly. Think of space-time being woven by these decoherence nodes. Near mass, the weaving is much denser, tighter. This density gradient creates a kind of structural pull. Objects in the less dense regions are naturally drawn towards the denser, more condensed regions.
So the structure itself guides them.
Yes. The river flows towards mass because the very fabric of the river is being created more densely there, creating a tendency for things to move towards that density.
So there is attraction. Objects do pull towards each other.
Yes. The observed phenomenon is attraction. DDTF explains it via this decoherence density thickening, while GR explains it via geometry. But the outcome, things moving towards each other due to mass, is the same.
And Newton. Was he right about attraction?
Newton was spot on about the observation bodies attract, and his math was brilliant for the time, but the mechanism, both GR and DDTF offer much deeper explanations than just a mysterious force acting instantly across distance.
So in DDTF, decoherence is really the star of the show. It's not just a side effect of quantum mechanics. It's the engine of reality.
That's the profound claim. It makes decoherence absolutely central, the source of space-time, time flow, and gravity. This really sets it apart from theories like string theory or loop quantum gravity, which often try to quantize gravity or space-time directly. DDTF says space-time emerges from quantum information processing.
But the challenge remains proving it, finding that unique prediction.
That's the key. Since GR works so well, any new theory has a very high bar to clear experimentally. It needs to offer something clearly distinguishable, or explain things like dark energy in a much more compelling, simpler way.
And analogies like the river model are useful steps along the way, helping us picture these complex dynamics.
Immensely useful tools for intuition, even if they aren't the final theory. They help us grasp the possibilities. So to sum up, DDTF is, well, incredibly ambitious. It's offering this potential quantum origin story for space-time and gravity, proposing a mechanism that might just explain why GR works, why the universe expands, and maybe even why it's accelerating, all from quantum decoherence.
And that river model still helps, right? Giving us that feel for a dynamic, flowing reality, not just static space.
Definitely a helpful image to hold on to.
So here's something for you, our listener, to think about. If reality, if space-time itself truly emerges from countless tiny quantum moments, from information becoming concrete, what does that really imply about the universe, about existence? What new questions pop into your head if every click of quantum reality is literally shaping gravity and time around us? Definitely something to ponder.